Hey, physics peeps. So we're going to talk about L diagrams today, and it's a continuation from conservation of energy and the energy skate park simulation that you guys played with the other day. When we draw L diagrams, they're really graphs that track the amount of kinetic energy and potential energy an object has. When we look at them, they're really similar to what was in that energy skate park simulation. And so they're going to look like bar graphs. And when we talk about kinetic energy, it relates to the amount of speed an object has, or velocity. The greater the speed or velocity, the greater the amount of kinetic energy. When something's not moving, we say its velocity is 0. But if we were to drop a person down that track, we know that as they move down, they might have a little bit of speed on that track at the beginning. And so their velocity is small, so their kinetic energy is small. That means that on the bar graph, this green bar was the kinetic energy. It's a small amount. But as their velocity increased as they go down, their velocity is larger. It means their kinetic energy is larger. So that green bar increases as they move down the track. When we talk about potential energy, it relates to the height above the ground level. When we say ground level, it's usually the lowest point on a track or on the path that an object is following. So in this case, it is the ground with that skate park. So when they get down here, we say their height is 0. That means that their potential energy is 0 down there. As we're going above that point, so like if the skater is right here, that means that they're above the ground and their height is rather large, so they have a large potential energy. When they have a smaller height above the ground, they have a smaller potential energy, and the blue bar represents that. So larger potential energy, the bar is larger, and lower potential energy, the bar is lower. That's kind of the gist of it. But this all does still go along with conservation of energy, meaning that the total energy of the system remains the same. So even though this skater might be moving down the track and they have different amounts of potential and kinetic energy at those points on the track, the total energy is staying the same. Kind of like what you ended up seeing when you kind of ran them up and down. The kinetic energy, potential energy, they transfer from one point to the other. Total energy stays the same. Yay. So as this person goes across the track, though, there is something that's kind of interesting that we find when they get to certain points, especially when they have the same amount of energy at points on the track. So if we kind of move them down, they'll you see that kinetic energy is increasing, potential energy is decreasing. As they move back up, potential energy is increasing again, and kinetic energy is decreasing. But notice that when they get here, up at the top, and as they go over here, that it's not that their potential or kinetic energy are 0, that they still have certain amounts of them, but they're just continually going up and down as they move along this track. When they get to the same height, though, that's when we say that their energies are equivalent. Because when you are at the same height, you have the same amount of potential energy. But if you have the same amount of potential energy and the total energy remains the same, you really have the same amount of kinetic energy. So I'll zoom in here and it'll be easier to see. Oops. Oop. Here, this thing. All right. This is what we want. So when the skater gets to this point, and this dotted line shows that they're at the same height as if they were at the top of that little bump. And they would be at the same height if they got over to this point. If you look at the bar graphs for each of these scenarios, their bar graphs are identical. Because they're at the same height, they have the same amount of potential energy, that blue bar. Because the total energy doesn't change, you really have the same amount of kinetic energy as well. So the key thing here is that when you're at the same height, you have equivalent energies at those points. So we say energy is independent of the path, meaning that it really doesn't matter how you get to that height. The amount of energy that you'll have when you get to that height is the same. It doesn't matter if you're going down or if you're going up or if you get going over a little hill, things like that. So that's kind of what we mean by energy is independent of the path. But what you need to know is that when you're at the same height, you have equivalent energies, both kinetic and potential. We can take that and be able to apply it to something like a pendulum that swings from the left side over to the right side. This is a problem that was on one of your assignments where you had to figure out the missing energies. And the key is the total energy has to stay the same. So if we look at this first situation, they tell you the potential and kinetic energy. This must have started from rest because it has 0 kinetic energy. But the total energy is just adding those together, and we get 10 joules. That means that the total energy everywhere else has to be 10 joules. But I can figure out some of these missing energies because the potential energy here was 2, it's at a lower point. The kinetic energy has to be 8 joules because 2 plus 8, that gives me 10. Here, when it's at its lowest point, this is what we would consider as ground level. Its potential energy is 0, and its kinetic energy has to be 10 because 0 plus 10 is 10. Over here, they don't give you either one of the potential energies, kinetic energies. And don't let this fool you, because when they don't give you either one, there is this little clue with the dotted line. And the pendulum is at the same position as it was over here, or the same height. Because it's at the same height, the energies are equivalent. It will have 10 joules of potential energy and 0 joules of kinetic energy. And that's how we fill those out. We can represent them with L diagrams. Those are shown down here. And so the kinetic energy, we just draw a bar for it. Well, if it's 0, there's nothing. But potential energy is 10. Usually when we say it's all potential energy, we try to draw that line up to the top of the graph. And that's kind of how we do that part. Over here, when there's a little bit of potential energy and more kinetic energy, we draw that over here. We'll draw a little line for potential energy. My kinetic energy, though, I'm not going to draw it all the way to the top, even though there's a lot more. Because remember the total energy, it doesn't change, but this needs to be less than the total energy. So I'm going to draw it and kind of eyeball it, whereas if I were to stack those two lines together, then I'll be up at the total. That's kind of what you do. When I get to this position, my potential energy is now 0. All my energy is kinetic. This is where I can draw it all the way to the top. And then when I'm at this very last position, that's where I can say kinetic energy, it's 0. My potential energy, I'm now back, all my potential energy goes up to the top. And that's how I draw those diagrams, and that's kind of what I want you to be able to do. What you'll do with your assignment is draw L diagrams for different situations. One is going to be for the skater as they go along that track from one side to the other, keeping track of their potential and kinetic energies. And if you need to go back to the simulation, you can go back and check that out. But you're going to draw 3 diagrams, this one, this one, this one, and you just show it on your paper. You'll have to show this on your paper and take a picture of it along with this next one with a skier that's going down the slope. I'll get you started on this one. So for this, you can draw 5 diagrams and you can really just have it all in a line on your paper. But for this part 2, you're going to start with the skier. It says that they start from rest at the top of the hill. So they tell you the kinetic energy is 0. Awesome. But because they're above ground level, ground level is down here. They have potential energy and all of its potential energy. When they start going down the hill, it's just like the skate park simulator, where as they go down, because now they have a smaller height. Up here, the height was large. Down here, they're having a smaller height above the ground. Their potential energy is decreasing. So I would draw a shorter line. But they are also picking up speed. So their kinetic energy is increasing. And if you kind of think maybe they're about the same, that's okay. Or if they're halfway down, that's all right. But as we go further down, we know that our potential energy is getting smaller because our height is getting smaller. So our line would start to look like this. I want you to complete this diagram for the skier. There's a couple things I want you to watch out for, though, is that these last two diagrams is what really sometimes gets people. You do need to finish up the kinetic energy here, but drawing the potential energy, kinetic energy here, and here is sometimes a little tricky. Don't let this one fool you. But then on this one, let me just kind of explain. When they get here, this looks really odd that they're coming down and it looks like they're landing straight down and they're going to break their legs. We're not talking about what's their kinetic energy, potential energy when they fall down and break their leg. It's more when they come in and impact the snow down here. We're going to assume that they just keep going along, all that kind of stuff. But when they impact the snow, what is their potential energy on impact? What is their kinetic energy on impact? Things like that. But yeah, that's kind of the gist of it. Make sure you talk to your teachers, ask them questions if you need to. And there are going to be other situations too that you will need to answer questions and draw other diagrams for on your assignment. But I think you guys will be really good. All right? So take it easy. Have a great day.